All right. So today we're going to start a new part of the course, section of the course, which is going to be about spontaneous symmetry breaking, in particular Higgs mechanism. So we have talked about spontaneous symmetry breaking in the past, but we're going to go more in depth with spontaneous symmetry breaking, focusing on spontaneous symmetry breaking in gauge theories, right? Because we discussed this for the case of global symmetry in the past. As usual, I'll start with a review of lecture 15. So if there are any questions, ask. In the previous lecture, we used background gauge field method, the background gauge field method, to compute the one loop beta functions. This is how you write beta function in English, of non-abelian gauge theory. We defined covariant background field D'Alembert, which was this object. It's a function of the representation, the gauge group representation is spin representation, right? This is covariant derivative with respect to the background gauge field. So, and then this is a background gauge field strength. And this is a Lorentz generator for spin J. And of course, this depends on the representation, right? They contribute to the one loop effective action in the following form. So the one loop effective action in its basic form will have the action, the regular action for the background gauge field, right? And the one loop corrections that associated with it will be log of determinants of these operators, right? We have one of those operators for gauge field fluctuations. So it's spin 1. It transforms in the adjoint representation. It comes with a power of -12 because these are bosons. We have F/2 log of determinant of spin half fermions. They transform in representation R, which we take to be fundamental and fundamental. Half because plus because this is fermions. And then finally, the ghost anti-commuting fields, which is ln of determinant of delta G0. This ghosts are scalar, but they transform in adjoint, plus because it's anti-commuting, right? So these log determinants are the differential operator as a function of the background gauge field, so you can expand it in the background field strength. And to the lowest order, the coefficient is precisely like the kinetic term, the background gauge field action. So the first term will give you quarter 1/g². This is the contribution coming from this log determinant. This is the contribution coming from this log determinant. This contribution coming from this log determinant. Sorry, this is this, this is this. And my NF should be capital. All right. But now these are log divergent. The structure of the divergence is logarithmic, right? So we argued using the Wilsonian approach to normalization as integrating thin momentum shells that if you take these coefficients and these functions and extract out the log piece of them, then beta function is just half C tilde G1 minus blah, blah, blah. So this is the form of the beta function. These coefficients could now be calculated just based on representation theory, and they have been calculated for spin J0 scalars. There are a third for Dirac spinners is -8/3. For 4 vectors, it's -20/3. This is the dependence on the representation. Good. So once you plug them in inside the beta function, you massage the equations, you get 11/13 of C2 of G, right? -4/3 NF T of R. For example, in the case of, so what was C2 of G? or I called it T2 of G, it's N. And for SUN, sorry, for SUN is N, right? So if NF is small enough, and T of R is half, right? T of the fundamental representation is half. So in the case of QCD, this becomes minus 11 plus 2 over 3 NF. This is how we ended up with negative beta functions or asymptotically free theories. Then we said that, well, now the theory makes sense in the infrared. It's a genuinely interacting theory, but then we have a little bit of a different problem. We have Landau poles in the IR at some finite energy. So the coupling naively, at least the one loop beta function, suggests that at some energy scale defined by the pole of this equation, by the zero of this equation, right? The coupling blows up at scale mu, the coupling blows up. So at this scale, the theory is strongly coupled and the physics is complicated. We know very little about it, but we do know that the theory confines. So then we went on the rest of the lecture discussing what confinement is. A gauge theory is confining if all finite energy states are invariant under global gauge transformations, meaning that if you take the, say, fermions and send them to e to the power of I alpha psi of x, right? This is a symmetry. One particular consequence of confinement is called confinement because you do not find individually charged states, right? This implies that a state with a single Q in it, a charged state, will have infinite energy, right? So if you take, you have these charged fermion, anti-charged fermion, fermion, anti-fermion with negative charge operators, and there's a potential. So there's a Wilson line that connects the two. That's a gauge invariant operator. So you could try to stretch these two guys so that at some point you could separate one of them to infinity, right? And that would be the way what it would take to isolate a single charge. But if you keep doing this in these confining theories, at some point it's energetically favorable to pair create charge anti-charge so that you end up with another charge neutral little state, right? So, and weak coupling, yeah.
And just a sanity check.
Yeah.
High energies, we're not in the confining phase anymore, right?
Yes.
So, and at high energies, can we detect individual forms? Of course.
Yes.
Of course. Just want to ask.
So deep in the UV, the theory is free, right? So the theory is just a bunch of these charged particles flying around. As a matter of fact, a simple way to calculate the potential between the charge anti-charge connected with the Wilson line is by considering this Wilson loop, where in Euclidean time, which has length tau, t, Euclidean time and separation r, because this could be understood as Euclidean time evolution by e to minus capital Th of q minus q. Roughly speaking, this gives you an energy or potential for this pair. In perturbation theory, we calculated this and found that, well, this potential E pair is just 2 alpha over pi epsilon UV. This is UV infinite, right? So this is the divergent self energy, but the actual potential, which is the energy, how the energy changes as you stretch the string that attaches them, is alpha over r, right? This is like a Coulomb potential that you expect in the UV. It's a gauge theory after all, right? So deep in the UV, the answer is very simple. And of course, if this is the potential, of course you could just isolate one of them to infinity by a finite amount of energy, so individual charged particles exist. Now, to understand how confinement comes about at infinite coupling in the IR, we can no longer use perturbation theory or the Gaussian framework. What we'll have to do is, the only other approach we had was lattice gauge theory, where in lattice gauge theory, we have a lattice, and to each link, we associate a matrix, and if it's an SUN gauge theory, an SUN matrix B, which we label a link, we're going to label it by the beginning and a vector alpha. As G goes to infinity, the gauge field action goes to 0, which means that all configurations are equally likely that the action that was initially giving us the weight in the path interval drops out, right? It just becomes I1 for everything. So you end up with just like a Haar random integral for every unitary on each side. I did not show you this, but I did not show this, but it's a homework problem for you guys to calculate this Wilson loop in this regime, and you will find that that this is proportional to the log of it is proportional to the area, which means that because the exponent is the exponent we're going to interpret as E pair times T. It means that the binding the potential is goes linearly in R, which is precisely the statement that if you want to separate them by infinite amount, you will need infinite energy. But of course, at some point, it becomes energetically favorable to pair create quark antiquarks. Short answer. Good. So this was our explanation of confinement. Crude. It's hard to do better. Any questions? Yeah.
This is like the model of the this computation of the expectation I do this like that's at order model which is
Yes. Very good. Correct. So when you go to sit as G going to infinity, right? It's a little bit like this. You see, there's this divergent self-energy term that you found, and then there was a correction to it. So these are large coupling effects. So there's a perturbation theory. You do a perturbation theory organized in 1 over G squared in a sense. It's not quite 1 over G squared, but it's like a perturbation theory around infinite coupling. Yeah, you'll see that. You'll see that. Good point. Thanks.
So if you build up the perturbation theory around infinite coupling, then your coupling constant, you should treat it as 1 by G squared for doing it perturbative, or because G tends to infinity. So how do you handle that?
Yeah, G goes to infinity, so 1 over G squared goes
1
to
over
0.
G squared is the parameter with which you work, right?
Roughly speaking. Yeah. Good. All right. So that was the previous lecture, and that closes our discussion. Of course, if you read more about this, you should, by all means. This closes the chapter on non-abelian gauge theories, and we're gonna move on to spontaneous symmetry breaking. So non-abelian gauge theories gave us interacting quantum field theories in the infrared. All right, that's very good. So we found gauge bosons as massless vector fields. These theories were naturally described in terms of there were gauge bosons that were massless. We know that massive vector fields have poor UV behavior. So far we have not found any consistent interacting theory we could get down for massive vector fields. Turns out that spontaneous symmetry breaking in gauge theories gives us low energy massive vector fields with good UV behavior, guaranteed by gauge invariance. So this is what we want to study. So far, we've talked about scalar field theory, right? You could give masses, that's perfectly fine. We naturally described interacting theories where excitations were massive vector fields, but they were, massless vector fields. Now, in nature, we see massive vector fields as well. And turns out that if you study spontaneous symmetry breaking in gauge theories, you naturally get a low energy massive vector fields. These are phenomena that are that happen all over the place. Superconductivity is an example of this, quantum Hall fluids, or electroweak theory. These are all gauge theories that are spontaneously, they all involve spontaneous symmetry breaking and gauge theories. So, the goal is to get a massive vector field, right, in the infrared. As a full and meaningful interacting theory. Before talking about that, I'm gonna review spontaneous symmetry breaking of global symmetries so that I can contrast it, right? Spontaneous symmetry breaking in gauge theories is a little bit different. It often goes with the name of Higgs mechanism, right? It's a little bit different. So by reviewing the global symmetry case, I'm going to contrast them. What is one main difference? Well, for one thing, global symmetry is an actual symmetry, whereas gauge symmetry is made up. It's a redundancy of the description. So a priori, it's not quite clear what it means to break gauge transformations, right? What does it mean? It's unclear what spontaneous symmetry, what is the symmetry breaking part? There is no symmetry in gauge theory, right? So that's going to be a big part of it. We also saw that spontaneous symmetry breaking of global symmetries led to massless modes that we call Goldstein bosons. Are there Goldstein bosons in spontaneous symmetry breaking of gauge theories? We'll see that the answer is no. All right. Consider the ON model. This is what the model we discussed in detail, right? So this is, there's a kinetic term. You have a vector field, phi A, and there's a mass term. We often take the mass to have like negative signs, so to arrange for the minimum of the potential, and then some phi 4 term. It's an n-dimensional real vector field. ON is realized linearly, right? It's not nonlinear, right? And here's a linear realization of ON, right? Orthogonal matrices. All right. If you look at the unshell action, look at the minima, the classical minima of this, it looks like, for the case of like phi 2, it looks like this Mexican hat potential, right? So phi A equals 0 is a vacuum, but it's unstable. And there's this set of vacua here that involve non-zero value for phi 1 and phi 2. Good. So we have these vacua. We could pick a particular one by choice of coordinates, picking v mu over square root lambda as like fixing the last element of it. Take the field phi and expand around this vacuum. Right? Now it should be clear that the mode that rotates you around this, rotates you around the minima of the Mexican hat, flat direction in potential. That's a massless mode. Whereas the mode that radially oscillates, that's massive. Right? So you expect massive and massless modes. All right. These pi k's are going to become the massless modes. They're going to be the Goldstein bosons. We saw that explicitly. We took the action and expanded it this way. We saw the potential for, so there's a mass that comes up for the sigma field, the fluctuations of V, right? But the fluctuations, the pi terms are massless. ON symmetry is spontaneously broken to ON minus 1. We did the counting, right? So there are how many massless modes? N minus 1 massless modes. N minus 1 Goldstein bosons. All right.
One question.
Yeah.
So we break ON symmetry and get ON minus 1.
Down to 1 minus
Down
1.
to
Yeah.
1 minus 1. Why do you stop there? Why not?
We could continue. Well, cook up another Hamilton. Well, the Lagrangian I wrote breaks it down spontaneously to O(n) minus one. We could cook up more fancier things that will break it further down. Nothing stops.
But in this example, why do you just stop at 1 minus 1?
Because that was those are the minima of this Lagrangian. I wrote down simple
So
Lagrangian.
if the what do you call it? The sigma fields weren't there, then we could. If the sigma fields weren't there, then we just have just have this O(n) minus 1 situation with whose minima are not at 0, and so we reduce it down further. Is that kind of
Sorry, I didn't understand. Say it again.
what I meant to say is that the reason we're stopping out is because we're already at the limit. Is that right?
Well, this was the Lagrangian I started with, and I found the vacuum of it, right? The vacuum were described by these guys.
Yeah. And then we basically recentered our fields P does that the vacuum
Yeah.
the balance is 0.
Yeah. So like around, I could perturb around this point, I could perturb around another vacuum, it won't matter. Because it's a choice of coordinate, they're related to each other by choice of coordinate. Field coordinates, right? But I can cook up all sorts of action that break it further down, right? All right, very good. So the continuous global symmetry transformation was sending phi A to this was a global transformation, leaving the Lagrangian invariant to the lowest order in epsilon for an infinitesimal transformation. Delta phi A, delta V, delta phi A is 0. Right? If I further take a derivative with respect to del phi B, I'm going to find this equation. This should be a familiar equation. This is just mass matrix, right? This is just a mass matrix. What is this term? This term vanishes. It vanishes on the minimum. It vanishes on the minimum because this is 0, right? So on the minimum, what you're dealing with is just del phi A, MAB squared is 0. Right? This equation, I just proved for you the Goldstone theorem. This equation is Goldstone theorem. If delta phi A is 0, it's still a symmetry transformation. Masses need not be 0. If del phi A corresponds to a variation of a variation that's no longer 0, so symmetry is no longer respected, right? It's not, then MAB has to 0. The mass of that has to massless. So every mode that's spontaneous, every symmetry transformation that's spontaneously broken must be accompanied with 0 mass. Must come with 0 mass, just a simple equation. The moment that, if it's respected, it's consistent to have 0 mass, right? So if you start with a massive theory, what you expect is that every mode, every continuous symmetry that was broken will give you a massless mode, right? So that's how the counting works. Spontaneous symmetry breaking always gives you massless scalar fields, right? And then we call them Nambu-Goldstone bosons for every symmetry. That n-1 counting was coming from counting the number of continuous symmetries that were broken, going from O(n) down to O(n) minus 1. Hopefully you remember how to count that. Remember that in spontaneous symmetry breaking, conservation laws are still there. The vacuum is no longer respected. The vacuum is no longer invariant under symmetry transformation. In fact, I'm going to try to say a few more words about that. This pi k, right, had to do with the massless modes, rotation and the motion in this direction, in the direction that's flat. right? This is the generator of the symmetry transformation. If I picked my, let me draw it here. This is my vacuum. This J will generate rotation around this. And these are also the modes, the vacuum fluctuations corresponding to this mode. So the generator of the symmetry transformation should take us from vacuum to an should mix the original vacuum with these one particle states of the Goldstone bosons. I should have such matrix elements, right? Because the distinction between these excited states and the vacuum is just symmetry transformation. I move around in the submanifold of vacua under symmetry transformation. You could see that explicitly if you calculate J mu A. This is J mu A. Yeah, these are Lie algebra, generators of the Lie algebra, right? Now on the solution, this is del mu phi A, TA phi 0. Phi 0 is the vacuum of phi 0 of J. So if I calculate 0 J mu phi I of P, I'm going to end up with this expression. So they mix. Yeah.
So, how do we get that? So I understand that you use the one that rotates.
This one? Okay, this one?
Yeah.
So how do I derive this? All right. What is this? Well, the answer is very quick. It's a Noether current. Go look up the definition of Noether currents for this transformation, and this is what you read. Right? Noether current for, but I mean, yeah. In general, we can think of this mixing of the Goldstone boson with the vacuum under the action of the current as having these coefficients FAB. There'll always be a derivative, right? Because there's a derivative in the current. This formula is very important, actually. I'm gonna give you a Feynman diagram way of interpreting this, but there's a non-perturbative aspect of it that I'm describing. Is that clear? So current conservation laws tell you that if this is J mu of X mu, if I take a derivative del mu of X with respect to this guy, I should get 0. That means that, well, that derivative will bring in another P down. I'm going to get minus P squared FAB e to minus IPX has to be 0. This is yet another way of thinking about stating Goldstone theorem. This is a weirder way of saying, fancier way of saying it, which you have to think a little bit about. This equation equal to 0 could be satisfied either by FAB being equal to 0 or by P squared being equal to 0. When P squared is equal, when FAB is not equal to 0, you have a setup where you actually have a Goldstone boson. P squared has to be 0, and that has a natural interpretation as a massless state. I leave that to you guys to figure out why that's masslessness. So this discussion was perhaps a little bit quick, but I invite you guys to think a little bit more carefully about it, because this lecture and the remainder of this lecture, next lecture, we're going to come back to this several times from different angles. The idea is that the distinction between the vacuum that are arbitrarily picked and the state with a bunch of Goldstone bosons is just symmetry transformation. So the simplest matrix element I can think of is a matrix element between vacuum and a single gold-sum boson for the current operator. That matrix element is non-zero. And we're going to be calculating that matrix. Good, yeah.
One step. So if I write by of previous, like say creation operator, EKP after the vacuum.
This one, yes.
Yeah, like so that is it.
Okay.
And then, so when I take the derivative of that equation, then isn't it like there's another operator sitting next to J, so maybe there's a contact.
There is another operators. Oh, you're saying that. Sorry, you're worried about the.
So if I write pi KP as A dot after the vacuum.
Yes.
So, and then I take the derivative of that matrix segment.
So first of all, at this level, your creation operators are going to be labeled by P, right? Okay.
Instead of a equal.
Okay, you can Fourier transform it. Then what?
So when I take a derivative of X, so it's gonna, I don't know, will it pick up a delta term, contact term?
There won't be a contact term here. So the contact terms, actually, yeah. There is a point splitting way of describing all of this. So I should not say that quickly that there is no contact. There's a point splitting way of describing all of this. Maybe I'll explain that next section. This expression is just true. This is just,
Yeah.
and we're going to calculate this actually in another way. If you don't get your answer by the end of the lecture, ask me again. But I'll try to include the different discussion of this from a point splitting point of view next lecture as well. All right. Good. Good for now. Now I'll explain that point in the simplest example, Higgs model example, Higgs mechanism. It won't be different. You'll see. So an important point, spontaneous, we're going to be studying spontaneous. So far I reviewed what we've done before. Spontaneous symmetry breaking, we like to study them in gauge theories because these are interesting theories in the infrared that are generally interactive. But gauge transformations are not symmetry, so it does not make sense to break them. It does not make sense to break the redundancy of the description. What is happening physically is the following. Gauge theory is some deep form of non-locality in the interactions of the charged particles, phi a's. Because we insisted on a local description, we introduced the gauge field, right? The gauge field was a long-range force that we introduced. It was massless, so that we can describe everything in local terminology. When phi a acquires vacuum expectation values, that is a set of spontaneous symmetry breaking. Now, the gauge field that you introduce as a redundancy of the description to describe these localities will no longer be long range, it becomes short range. That's the physics of what's going on. Right? So let me recap. Engaging theories, there is no symmetry. All we have is a bunch of particles whose interactions are have some non-local features, right? To describe that non-locality, we introduce these fictitious gauge fields. They introduce a long-range force, right? They're massless, they had long-range forces, right? What goes on in spontaneous symmetry breaking is that these phi's, they require one-point functions, vacuum expectation values. You still have these non-local features. But if you insist on like locally representing them, the gauge fields that you introduce are now first massive, second, they're short range. They're no longer long. The fact that their masses had to do with long range. Now it becomes short range and they become massive. Is that clear? So physically something is going on, right? It's not a symmetry that we're bringing. So in explaining all of this, it is crucial to remember, up until now, we have been equating two things together. Gauge theory implies that the gauge boson is massless. That is too quick. Ward identities were gauge theory, gauge transform, invariance. Gauge invariance implied masslessness of the gauge boson modulo some assumptions. I'm going to remind you of those assumptions, and those assumptions were violated mildly here. Importantly, that one of the assumptions was that there is no massless mode in the spectrum. So we're going to go through that. So this is the calculation we did in part 1 of last semester at the end of it. So so this is just to build. We're going to build up to this, but to just have the picture in mind, gauge theory gauge invariance does not always require the gauge boson to be massless. Under some assumptions, it requires it to be massless. Spontaneous symmetry breaking is the counterexample. It's set up where you can have gauge invariance. Ward identities are checked. You still have mass for the gauge field, right? That just means short range. Interactions are short range. We're going to see later in this course, when we discuss anomalies, examples of theories where QED in 2 dimensions is an example, where you have a gauge theory, you have a gauge boson, photon, but it's massive. That theory also as like a counterexample, right? It's called Schrödinger model. That will be our canonical example of discussion of anomaly. All right, is that clear? So to start simple, let's start with abelian gauge theory. Spontaneous symmetry breaking of abelian gauge fields is an important theory. So if you take QED and spontaneously break the symmetry, what theory do you obtain? Sorry? That's a theory of superconductivity. That's why spontaneous symmetry breaking was discovered by those guys. Anyway, consider the abelian gauge theory. Yeah, you know what? Have you learned superconductivity? No? All right.
We went for once in a condensed matter class, but I don't remember any.
All right.
But I don't think we did.
Maybe I should include the homework. Yeah. So. All right. Here's the abelian gauge theory. So we're going to start with the abelian gauge theory, the simplest case possible. U1, right? The U1 meant that this phi field is complex. This is the gauge transformation. This is the electron or charged. We're going to put this Mexican hat type potential. Well, it's not Mexican hat, but like, you know, like phi square, phi 4. There's a negative sign to arrange for spontaneous symmetry breaking. So it's the field phi that requires a vacuum expectation value. The non-uniqueness, so now if you take this vacuum expectation value, multiply it by phase, right? It's another vacuum. So this phase is the S1, this picture I've been drawing, right? This phase is the S1. And A mu has to be 0. This is the vacuum solution.
This even for I alpha here is constant, right? The last expression.
No, as a matter of fact, this expression, this.
Yeah.
No.
Oh, this also.
I will comment on this. I'll comment on this.
P exactly is like the ON one.
Sorry, well, just one little thing. If it's constant, if this is zero. Right? If I make this function space dependent, this will have to be non-zero. You were saying?
P is the ON one.
No, this is just a complex field.
So just to
It's U1, right? U1. It's a complex field, e to the power of I alpha. I alpha, right? It's just a phase. That's your gauge. Yes, you can write it as an O2 model, yes. And in a second, I'm gonna write it as an O2 model. But I'll have to introduce these i's, right? Plus I, phi 1 plus I, phi 2, blah, blah, blah. You'll see actually that the fact that, yeah, there's a trick to use. Yeah. But does this make sense? Like if you could promote this to an alpha of x at the cost of this guy being non-zero. But the point is that you can set the gauge field equal to 0 and there's still a phase here. We're going to define our vacuum. We have to arbitrarily pick some value of alpha as a vacuum, right? We're going to pick alpha equals 0 and expand around it. Here's where I'm going to introduce phi 1, phi 2 plus I, phi 2 notation. All right, here is V of phi, and here is the covariant derivative expanded. Now, the V of phi doesn't have any surprises, but the covariant derivative expanded is interesting. This is the real field, this is the imaginary part of the field, right? Fluctuating field. They come with like usual kinetic terms. A mu pick up a mass term from the vacuum of phi, from this, right? Half E squared phi naught squared. Then there's a term that couples A mu to del mu to phi 0. Now, does this term look familiar? Does this term look familiar? This guy sitting next to A mu. No, not yet. What if I call this J mu? Yeah. We'll get there. So this is a term that came out of the expansion of the covariant derivative, right? So let's for now ignore it. For now, let's focus on the masses. Phi 2 is massless. Phi 1 is massive, and the gauge field is massive. If this were a global symmetry, global U1, right? Phi 2 would have been the pi field or the Goldstone boson. It will have to remain massless, right? Phi 1 would have been the physical. Good. So it seems like we managed to give a mass to the gauge field. We have to understand what the hell does that mean. This looks like a Goldstone boson, and then this is phi 1. Good.
What's the gauge transformation in this case? Like, how would you write it down in terms of these 5 and 5 to 2?
In terms of the phi, oh,
Yes. So basically, I like write down the E for I alpha in terms of like 5 by 2.
yeah. You just expand. You just say that. Take this expression, right? Send it to e to the power of I alpha. Same expression. Phi naught just drops out. So phi 1, phi 2 are transforming into gauge transformation.
How you are breaking down phi in terms of phi 1 and phi 2?
How am I breaking it? Sorry.
How you are breaking phi in terms of phi 1, phi 2, and phi 3?
Phi is a complex field. I'm expanding it around its vacuum expectation value. This is a fluctuating field that I just decided it's a complex fluctuating field. I'm going to write it as phi 1 plus I phi 2. Okay. Now let's focus on this term. Phi naught is a vacuum. You haven't seen any term like this in the past. Why? Because this is the fluctuating field. This is the gauge field. These are both fluctuations, right? So it looks like it will contribute to the following Feynman diagram. right? It couples the gauge field to a fluctuating field. It's a 2-point function. That is odd, right? And because this was the mass of the gauge field, this is what it looks like. IMAK mu. Good. We'll come back to this in a second. Actually, let me say it very quickly. This looks like a gauge boson, but it's not. Sorry, this looks like a Goldstone boson, but it's not a Goldstone boson. This looks like the gauge field that's massive. So what's going on is that this term tells you that phi 2 mixes with the gauge field at the kinetic level. So your Hamiltonian, your kinetic term needs to be rediagonalized, right? And once you diagonalize it properly, this phi 2 is no longer the correct propagating degree of freedom, right? The proper degree of freedom, this guy is going to be packaged next to the gauge field. It's going to be part of the gauge field. This diagram is an indication. But you knew that. The gauge field, massless gauge field, had 2 degrees of freedom in 4 dimensions because it was massless. Spin 1 massless. The moment you gave it mass, it should have 3 degrees of freedom. So the degree of freedom should come from somewhere, but it's coming from here. So the counting of the degrees of freedom is correct, right? Sometimes people say that the Goldstone boson was eaten by the gauge field. These words don't mean much in a sense, right? You just have to properly diagonalize to define what a particle is. You have to properly normalize or diagonalize their kinetic term. That's your definition of particles, right? In this case, before spontaneous symmetry breaking, your degrees of freedom was a massless gauge boson, right? And two ingredients for elements of phi. Here, it's a massive one, and phi 2 is just disappeared. That's not a degree of freedom. There's a massive vector field which has 3 ingredients. Yeah.
For the kinetic term which couples the A mu and del mu, phi, notice the phi, it's only the phi 2 term which pops up, not the phi 1.
Correct.
Is there any physical significance or is calculation?
No, it's very important. Phi 1 is this massive mode. This is the one that we want to interpret as a Goldstone boson. Right? There is no Goldstone boson. The interpretation of phi 1 and phi 2, even in the case of global symmetry, was very different. Right? One of them is a motion in the flat direction. It's only the flat direction one that mixes with gauge transformations. Right? We just argued for that. J mu mixes with pi.
Oh, is this because we're taking the vacuum explanation value to be real? That's why the phi 1 has mass and phi 2 doesn't. Is that?
Yeah, that's one way of saying it. Yeah, when I expanded, yeah, you could.
Okay, and that's why the phi 2 couples up with there. Okay.
Yeah. Phi 2 is like, it's important that it's around alpha equals 0 as perturbation in the gauge direction. All right, all good? So what do I need to explain? I need to explain how is it possible to preserve gauge symmetry with a massive gauge field. I still have to justify, right? All right, so let's build towards it. I'll show it at the end I'll tell you in the end that when we went through the analysis that connected word identities, gauge invariance with masslessness of photon, I said a set of words that won't apply here. But let's go through this a little bit slower. So this is the propagator for the gauge boson, right? So there will be this term, but then now because in Feynman diagrams I have stuff like this that contribute like this way. All right. This is massive. Let's say it's proportional to Adam mu. Let's work in the gauge where C is 1. What does this give? This gives MAK mu I over K squared minus MAK nu. Remember that it's important. This form, when you write it this way, you could repackage it in this form, which looks like okay, right? The whole thing became a gauge transformation change. In that, it was important that this guy was massless. If this guy had a mass, we would not have been able to get rid of it. It would have given the photon a mass, and that would have been horrible. This looks like still kosher, right? It's still transverse. It's massive, but remains transverse. Because, crucially, this guy was massless. Now, as I'm saying this, I'm also repeating that it's incorrect to view this as a degree of freedom that's massless. It's not an independent degree of freedom. It's mixing with the gauge field, right? But if you were to draw these Feynman diagrams and treat it that way, this is like the caveat. Good? So let's do this a little bit more systematic.
So
Yeah.
things would work out even if we didn't diagonalize correctly.
No, that diagonal. Yeah,
But the interpretation.
but you should diagonalize.
Yeah,
You
of
really
course.
should diagonalize. You'll get yourself into a lot of trouble. I'll diagonalize in a bit. If this were global symmetry wrecking, phi 2 would have been the massless Goldstone boson, but in the gauge theory, it mixes with a mu in the kinetic term. So to describe particles of the theory, we need to diagonalize the kinetic term. So what does the kinetic term look like? I can write it this way. I can package it this way. The a mu term looks like it has a mass term like this. I packaged it all together. Phi 1 has this is massive mode. Phi 2 is a massless mode. And then there's this off diagonal term that couples them. Right? And I'm just writing phi 1, phi 2, a. All right. Is this clear? So first thing, is this gauge invariant? Oh, actually, no. First thing to notice is that phi 1 decouples. Right? So phi 1 and phi 2 are their story is very separate to start from the other. Phi 1 decouples completely. So I can focus on A2 and phi 2. Is this gauge invariant? For this to be gauge invariant, what I needed is that now I can no longer view A nu and phi 2 as separate. Well, A nu as the gauge degrees of freedom, phi 2 as gauge degrees of freedom. What matters is that this 2 by 2 matrix has a 0 eigenvector. So that's not invertible, right? We saw that was a property of gauge invariant theories, right? The propagator was not invertible. All right, here's the 0 eigenvector. Phi 0 minus I over 2 k nu. The kinetic term is non-invertible. This is a pure gauge mode. We also have 3 vectors with eigenvalue k squared minus ma squared. That is a gauge field, actually. I trust you guys to go through the analysis, and we'll go through this analysis. Next lecture, we're gonna quantize this theory, spontaneously broken gauge theory. But as I said, phi 2 is would have been Goldstone boson degree of freedom. There were 2 massless vector degrees of freedom. They combined into a mu, which is a massive vector degree of freedom. This a mu is the 3 vector with this eigenvalue. I haven't done it here yet. Okay. Good. Is this part clear? Yeah.
So the fact that the propagator was not certainly the propagator, but yeah, propagator had a 0 eigenvalue. Very questionable motion. The inverse was probably defined to be propagator.
Yeah.
Because we had a massless mode, we said you have the 1 over k squared and so.
It's because of word identities. Word identities are the things that tell us that the property is not invertible. Because once whatever the propagator is, contracted with Q mu, it should become 0. Right? So this whole, the form of the propagator I've been playing with, remember, we wrote this stuff for C1 plus minus CRI and whatever minus. These are the two tensors such that whoops. Well, anyway, you know. That's because of Ward. So we need gauge invariance should be respected.
So it's like a different movie. Order into the
Yeah, well, yes, Ward identities are the conservation laws. Or like operator versions of, like. I mean, that's how we derive them, right? We derive the J mu corresponding to gauge theory, the current, and del mu it had to be 0. Okay, very good. So this analysis was a little bit confusing because I wasn't gauge fixing. This is a gauge theory after all. In fact, there is a gauge called unitary gauge, which completely gets rid of phi 2. This is the case where you pick phi x to be real everywhere. So you could pick that alpha of x in your solution such that phi that the fluctuating field is real everywhere. So it's not, you shouldn't be surprised that phi 2 was not a physical degree of freedom. Right? It was gauged anyway. It could be gauged out anyway, completely. In this gauge, the action takes the following form. It's just a real scalar field, which is massive. There's a mass term for it, right? Remember that phi 1 always decouples. And then massive gauge vector field. Higgs mechanism is the name of the following for the following phenomena. Spontaneous symmetry breaking in gauge theory generates a mass term for gauge boson. That has a name. This phenomenon has a name. It's called the Higgs mechanism. So to repeat, the physics of it is that no symmetry is being broken. The charged matter acquires one-point functions, which means that if you insist on a local description, you'll have to use massive vector fields now. Interactions are short range. That's it. And you still have gauge invariance, right? Of course, because you made up degrees of freedom. You still satisfy Ward identities. All right. Any questions? So in the remainder of the lecture, what I want to do is I'm just going to quickly go through a non-abelian version of this very quickly, high level. Next lecture, we're going to quantize it, the non-abelian version, all of that, fun and that. I'm going to comment on that matrix element of 0 J mu A I B. What do you call it? Q K P L, right? I'm going to comment on this guy. And I'm going to remind you the QED calculation where I told you we were okay in renormalization in QED for one loop. QED at one loop was not introducing a mass term for the photon. I'll repeat this set of words I said, and you will see there's a caveat to that. It's important for me to say that because we'll come back to that in anomalies, and you will see another time that caveat is important. QED in 2 dimensions is a gauge theory where the photon is massive, non-perturbative. It's a 2D theory, right? It's super renormalizable. So you could actually calculate it. The mass of the photon is non-perturbatively determined. It's called Schrodinger model. And you could calculate. It's non-zero. It's perfectly consistent with everything. It's a very 2D phenomenon. All right. How does the non-abelian story generalize? Well, you wouldn't be surprised that I start with same action, type of action, right? Sometimes people say that this action was found, but starting with the, for example, ON model and gauging the global symmetry. Hopefully it's clear what those words mean. Gauging a symmetry, right? The words are hopefully clear. That is a set of words, right? Once we come to anomaly, we might or might not comment on that, so those set of words. But for now, it's just methods to write down Lagrangians, right? So the gauge transformation is an infinitesimal gauge transformation is this, right? And here's the covariant derivative. To find that funky, oops, yeah, to find that funky, well, I think coupling like this, what I did was I took the covariant derivative of phi j squared and expanded it, right? So I'm gonna do that. Here is the first term, second term, and then there's a g squared term, right? This is g squared TATP. This is TA, it's the diagram. You wouldn't be surprised to know that these two terms are the origin of the trouble. I haven't done spontaneous sense breaking yet. I have not introduced a background gauge fully yet. Now I'm gonna do it. I'm gonna take phi j and write it as phi 0j plus chi as a fluctuating field. This term will give me a mass term for the gauge boson. Non-abelian gauge boson, right? Because I put phi 0, phi 0. That will give me a mass term for the gauge boson. This is the mass matrix. Yeah.
Again, the gauge field is set as like the vacuum expectation that is zero.
Yeah.
Expanding the wrong.
Yeah. Sorry, I should have said that. Yeah. So this is the mass term for the gauge field. Mass matrix, right? Of course, it's labeled by A, B. A and B are the generators, the Lie algebra generators. Every unbroken generator, TA, acting on phi naught equal to 0, gives a 0 eigenvalue for this mass matrix. Is that step clear? This is a direct generalization of what I said before. What I said before, let me show it to you, was this. I showed that this is an equation I derived before, right? This is a variation of the gauge variation, the gauge transformation of the field, MAB squared, right? And I said if the field is invariant, so it's not broken, MAB need not be 0. If it's invariant, it's del phi A is 0. But when it's no longer invariant, it's broken, its corresponding MAB has to be 0, right? So in this setup, there are these TAs that appear. This TA is the analog of that del phi, right? We also, in this expansion of del phi squared, we found these two terms. Now, when you evaluate these two terms, they look like J mu. This is J mu, by the way. This is the non-abelian J mu coupled to A mu. If you evaluate the J mu on the vacuum, Some of these guys will get 5 zeros, and you end up with this expression. This is the non-abelian analog of MA E phi naught A mu del mu of phi. 2 over there, right? This is precisely that. It's a 2-point function between the non-abelian gauge field and the propagating degree of freedom. So there's a non-abelian version of this precisely the same phenomenon. So it contributes in the following way to the path integral. It corresponds to the following comment. There's a TA associated with this, right? Good. There's P mu and TA in there. K mu. As before, you could ask about this diagram as a contribution to the propagator of the gauge field. Well, this guy's massless, so it's I over K squared, this, you repackage everything, you get I MAB squared, something that satisfies word identities. It's all good. As before, actually, B. Sorry, do I want to write it this way? I think I want to put a B in here. Yeah, I want to put a B in here. What is K? That's a dumb label, sorry. As before, I can interpret this guy as a matrix element, 0 vacuum, one pi with J mu of A. This is like the gauge theory analog of that. I'll come back to this. I'll come back to this.
So which diagram will you take this?
This one? Sorry, which one? Sorry, what was the question?
You're saying that that diagram is that matrix element.
This.
But like, where is the gauge or in that matrix element? Oh, it's that, okay.
All right. Let me see. Yes, I'll have. Okay, so we're gonna come back to non-abelian gauge theory, spontaneously broken, next lecture, and quantize it. Over there, we're gonna properly diagonalize everything, be very careful with degrees of freedom. Everything is going to, I promise you guys, I'll be reverse about everything. But before doing that, I want to remind you a quick discussion we had at the end of QFT1, where I argued that word identities will tell you that at one loop, photon will remain massless. We pretended that was required, that was a must for a gauge invariance. That's in QED a must. But we'll see that. So what was the argument? Here is the word identity. Word identity is implied that the 1 pi propagator 2 point with contracted with Q mu has to be 0. Let's call this I pi mu nu Q. This is what we did last time. Non-perturbatively, it must have the following tensor structure. For some pi Q. Therefore, you could show that you could resum this as a summation over 1 pi, the next, you remember what I'm talking about, right? So it comes down as a numerator of this form. Now, photon will remain massless if pi of Q, calculate to arbitrary loop, has no poles as Q squared going to 0. We saw that in QED at one loop by explicitly write down what this pi of Q was. Pi of Q was just one integral in which coming from was an integral where the fermion was propagating, going around the loop. The fermion had a mass, and that was, the fermion had a mass, and that was important. this term in QED at one loop we calculated it, and it was no, it had no poles at Q squared going to 0. But if this loop that we're discussing that contributes to pi q involves a massless particle, it could have 1 over q squared. So if you have massless modes in your spectrum, it is possible to preserve gauge invariance, right? And ward identities, and give mass to the gauge field. In general, having massless modes in the spectrum is an awful thing. It sounds terrible. Spontaneous symmetry breaking of gauge fields naturally gives you a setup for this. QED in 2D does give you a setup for this. It's not a good idea to just introduce by hand like massless gauge massless fields. Charge fields. That's not a very good idea. Think about why. All right, yeah. So let me summarize then. I think this is my last slide. Yeah. So in summary, what did we do today? Today we said that non-abelian gauge. We started spontaneous discussion of spontaneous symmetry breaking gauge theories. We said that gauge theories gave us interacting massless vector fields, but the term massless was kind of loaded. In fact, gauge theories give us massive vector fields as well. Interacting, nice and good. It's just that if the field phi, if the charge fields acquire 1-point functions, spontaneous symmetry breaking happens, then the gauge field description will be interacting and will include massive vector fields in the spectrum. The connection between masslessness and gauge invariance ward identities came through this extra level of this extra argument that was saying that this pi q in the 1 pi 2-point function had to be smooth as q, had no poles as q squared going to 0. That was the case for when there were massive fermions running in loops and at one loop vacuum polarization. Okay, so another thing that we said was that what is the physical interpretation of spontaneous symmetry breaking in gauge theories? Because it's not a symmetry. It's just a statement that if you give vacuum expectation values to a charged field, still not local theory. If you insist on a local description, you'll have to introduce massive vector fields, and the interactions are short range. Right? No magic happens. And then we said that one manifestation of it is that in gauge theory, if you're not when you spontaneously break symmetry, there is a mixing in your kinetic term between the gauge field and what you thought the charged matter fields, and you have to properly diagonalize that thing. There is no Goldstone boson in gauge theory spontaneous symmetry breaking. Right? All right, that's all. Any questions?
So in all of this, one has to start with the mass of the non-gauge field. For example, if we over here, we have to start with the mass. So that's like
You're asking whether I can cook up another spontaneous symmetry breaking potential without phi squared term. I think I can.
like 5 minutes plus.
Yeah, I can cook up things.
So
But it's unnatural because when, as you recall, if you're talking a scalar field, you should just like allow all the, if you're allowed terms, you should allow all of them.
I was wondering, like, is there a way to not start with a master, but like somehow get a symmetry which gives master to the.
It is possible, but you'll have, that setup is contrived. A symmetry must forbid the master. right? Remember that we're not writing theories in vacuum. You write down an action. Where is that action? At what scale is that action? Right? If you say that this action with a certain scale, I just run the RG a little bit further and think, oh, there is a master. So there must be any term that you did not put in there must be forbidden by symmetry. Right? So that's a basic principle. Right? And there is a reason that spontaneous symmetry breaking is so natural. Because the first few terms do give it. And the first few terms in the scalar field theory are allowed, no symmetry forbids them. Unless it's a nonlinear sigma model. Nonlinear sigma models are different stories, right? Where interaction is fixed by some sort of nonlinear realized symmetry. But some symmetry principle is the only way to go. And for better or worse, phi scalar field theory is just anything else, right? Any other questions? So in the remainder of I'm planning on one more lecture. Hopefully we'll wrap it up on spontaneous symmetry breaking Higgs mechanism, quantization of it. Then we'll move on to standard model. There will be 2-3 lectures on standard model. That will be hopefully the end of our all discussions before moving on to non-perturbative methods. And the rest of the semester is going to be a non-perturbative methods, and I'll try to give examples from standard model or physical. There are non-perturbative things we know about these perturbative theories around us. So the non-perturbative physics we discussed, we're still going to use these examples of interacting field theories we construct. Remember that we said that QCD exists. It doesn't mean that we understand. All right. Thank you so much, guys.